Hello students, in today's video, let us have a brief understanding about the basic concepts in electrodynamics. We will specifically look into the Maxwell's equations and we will try to formulate the inhomogeneous wave equations based on the Maxwell's equation. So we know Maxwell's equations are a set of four equations that govern the basics of electrodynamics. So what are the four basic equations? We have del dot E equal to rho by epsilon 0. So this is the Gauss's law. Then the second equation is del cross E equal to minus dou B by dou T. So this is Faraday's law. And the third equation is del dot B is equal to 0. And this equation does not have a specific name. And the fourth equation is del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. So this equation is Ampere's law, and each of these equations gives how magnetic and electric fields are generated by charges, currents, and by the changes of the fields. So first equation gives how electric field is produced by charges. Then the second equation implies how an electric field is developed by changes in magnetic field. Then the third equation implies that magnetic monopoles does not exist, or that magnetic fields always form closed loops. And the fourth equation implies that either a current or a change in electric field can generate magnetic fields. So these equations broadly govern everything relating to electrodynamics. So these are the fundamental principles of electrodynamics, and they just say how electric fields and magnetic fields are produced from charges, currents, and changing fields, magnetic or electric fields. Now these equations also imply at many other properties of electric field and magnetic field. For example, if we take the equation number 3, del dot B equal to 0. So that implies that magnetic field can be represented as the curl of a vector potential, del cross E. So this is a mathematical assumption. If divergence of a vector field is 0, then that vector field can be represented as the curl of another vector potential. So del dot B equal to 0 automatically implies that magnetic field can be represented as del cross some other vector function. We call this function A as our magnetic vector potential. Similarly, we have del cross E equal to minus dou B by dou T, right? In the electrostatic case, that means if nothing is changing with respect to time, we have del cross E equal to 0. Because no time dependence is there, that is B is not changing with respect to time. That means this term is 0. So this is in electrodynamics, and del cross E equal to 0 is in electrostatics. Electrostatic means no change with respect to time. Electrodynamics means something is changing with respect to time. Dynamic, the system is dynamic. So del cross E equal to 0 actually implies that electric field can be represented as gradient of a scalar function. So this is another mathematical formalism. When we are thorough with the gradient, divergence and curl in mathematics, we actually deal with these kinds of problems. Like if del dot B equal to 0, it's quite natural that we can represent B as del cross A. Similarly, if curl of a vector function is 0, then that vector function can be represented as negative gradient of a scalar function. So please be thorough with these kinds of terms: divergence, curl, del cross curl, and gradient. In electrodynamics, del cross E is not equal to 0. In electrodynamics, we have del cross E equal to minus dou B by dou T. So I can actually reformulate that equation like del cross E equal to minus dou B by dou T, right? So this is equal to minus dou by dou T of what is B bar? B bar is del cross A bar. So taking this to the other side, I will get del cross E plus dou by dou T of del cross A is equal to 0. So I can actually exchange between dou by dou T and del since they are mutually exclusive. It does not depend the order. They are commutative. So we can write del cross E plus del cross dou A by dou T is equal to 0. So this implies that del cross of E plus dou A by dou T is equal to 0. So in electrostatics we have del cross E equal to 0, whereas in electrodynamics del cross E is not 0 but del cross E plus dou A by dou T is equal to 0. So what does this mean? This means that E plus dou A by dou T should be equal to minus del V. Here, since del cross E equal to 0 in electrostatics, vector E, electric field is equal to minus del V, whereas in electrodynamics, electric field plus dou A bar by dou T is equal to 0. So this implies that electric field is equal to minus del V minus dou A bar by dou T. So this is the electric field in the case of an electrodynamic system, a time-dependent system. Similarly, we have obtained the equation for magnetic field in terms of vector potential, and the electric field is now represented in terms of scalar and vector potential. This potential V is called scalar potential and vector A is called vector potential, because these vectors determine the values of electric field and magnetic field. These vector and scalar, these potential determine electric field and magnetic field. Here you can see electric field is a function of potential, scalar potential and vector potential. Similarly, magnetic field is a function of vector potential. So these two equations, we have modified these two equations, equation number 2 and 3, and we have obtained another set of equations. So equation 2 implies electric field can be represented as a function of scalar potential and vector potential. Similarly, the third equation implies that magnetic field can be represented as del cross A bar. So we have reformulated the second and third equation. I hope you have some basic idea about these equations. If you are not thorough with these equations, just go to other reference videos and understand these equations. Now, we can actually substitute these equations, that is this equation for electric field, into the first equation, right? The second equation, I have found electric field from the second equation and I can substitute for E into this equation. Similarly, we have B bar here and we have found the equation for B bar from the third equation. I can substitute for B bar into this equation from third equation. Similarly, for electric field here, I can substitute from the second equation. So what have we done? So this is a common mathematical trick. Suppose you have 2 or 3 equations having same problems, like suppose x plus y equal to 3 and you have y equal to 2. These are two sets of equations. How can you combine these two equations into one equation? Substitute for the term from here into first equation, right? So x plus y equal to 3 and y equal to 2. This can be combined as x plus 2 equal to 3, and which implies x equal to 1. So this final equation actually consists of the concept from two of the equations. This has combined the concept from two equations. Similarly, we are doing one trick. We have 4 Maxwell's equations. We are trying to reduce that equations. And if we have to do that, we try to find out electric field and magnetic field from 2 equations. And we substituted for electric field and magnetic field in the other equations. So in that way, you can reduce these 4 Maxwell's equations into 2 equations. And those 2 equations are called reduced Maxwell's equations. So let me write that equation. I think you have to derive that equations in the first module. As of now, just for the sake of continuity of concept, let me just state these Maxwell's equations in the reduced form. So those are given by del square V plus dou by dou T of del dot A bar equal to minus rho by epsilon 0. Similarly, the other equation is del square A bar minus mu 0 epsilon 0 dou square A bar by dou T square minus del of del dot A bar plus mu 0 epsilon 0 dou V by dou T is equal to minus mu 0 G. So you do not have to worry about the length of these equations. These equations might seem a very lengthy and complex equation. You do not have to worry about that. Just think that you know the 4 Maxwell's equations, right? These reduced Maxwell's equations are just 2 equations that state the concept of 4 Maxwell's equations in a shortened manner, in a very simple manner. So in every idea that we have about Maxwell's equations is actually contained in these 2 equations. So that's why they are called reduced equations. And the 4 equations are actually made to be contained in these 2 equations. So that's about Maxwell's equations in the reduced form. Now let me also mention another interesting concept about the Maxwell's equations, electric field and potential. So that is gauge transformation. So I will just state the concept here. You will have to study it in detail in the first module. So gauge transformation is that, the concept is that we have talked about vector potential and scalar potential, right? These vector potential and scalar potential does not have any physical significance when we come to measuring any quantity. We actually measure the electric field and the magnetic field. Those are the quantities with real physical significance. Vector potential and scalar potential have significance in the context of electric field and magnetic field. So maybe you have heard that the scalar potential is not unique and we can actually add or subtract some constant to this potential. So that will not make any change in the value of electric field. So this gauge transformation implies that the vector potential and scalar potential are not unique. You can change the values of vector potential and scalar potential in certain way so that the electric field and magnetic field is still unchanged. So those kinds of transformations that we bring to vector potential and scalar potential without affecting electric field and magnetic field are called gauge transformations. So I will just mention that transformation here. So they are given by A dash equal to A plus del lambda. So this simply means that any vector potential, if you can find any vector potential that satisfies the equation B bar equal to del cross A bar, another vector potential can be found by adding a del lambda, and if you substitute and find del cross A dash, that will be again B bar itself. So there is not one unique A bar. There are plenty of A bars, plenty of vector potentials that can be chosen without affecting the value and the strength of the magnetic field. So that is the concept of gauge transformation, and this is the transformation that we can bring into the vector potential without affecting the value of magnetic field. Similarly, we can also bring a change to the scalar potential, which is B equal to V minus dou lambda by dou t. If you bring this change to the scalar potential, it will not affect the value of electric field. So these two changes, when combined and given to the electric field, the final value of electric field will not be changed, will not have any change. So these sets of equations give us a liberty to choose vector potential and scalar potential. You can choose vector potential and scalar potential as per your convenience. If one vector potential is not suitable for calculations, you can change that to another vector potential. Similarly, if a scalar potential is not suitable for some calculation, you can change that scalar potential to another value by subtracting minus dou lambda by dou t. So that is the concept of gauge transformation. So you will study in detail about these concepts in the first module. I will just summarize about these concepts now. And two particular gauge transformations that are available are Coulomb gauge and Lorentz gauge. So what is Coulomb gauge? Coulomb gauge is given by the condition del dot A bar equal to 0. So as I have mentioned, A bar is not unique. You can change A bar to different values by adding a del lambda, and by changing A bar, you can choose one particular A bar that will give you del dot A bar equal to 0, right? You have different values of A bar. A bar can be changed to A dash. It can be again changed to A double dash or triple dash by adding and subtracting del lambda. And for one particular A bar, you might get del dot A bar equal to 0. And that condition and that A bar is used in Coulomb gauge to get the final results. So del dot A bar equal to 0 is the Coulomb gauge. We choose that particular A bar for which del dot A bar equal to 0 in the Coulomb gauge. Similarly, for Lorentz gauge, the condition is del dot A bar is equal to minus mu 0 epsilon 0 dou V by dou t. So you can choose one particular A bar, and for that A bar, we should get del dot A bar equal to minus mu 0 epsilon 0 dou V by dou t. And this condition is called Lorentz gauge. So why do we use this Coulomb gauge and Lorentz gauge? We use this gauge to bring simplicity to our equations, simplicity to our conditions. For example, we have actually written the Maxwell's equations in the reduced. These two equations are very lengthy and seems to be very difficult to handle. But we can actually make small tweaks in this equation, small changes in this equation without affecting any of the physical values by bringing in this Coulomb gauge and Lorentz gauge. For example, if I bring this Coulomb gauge into the equation, into the Maxwell's equation, the Coulomb gauge is that del dot A is equal to 0, right? So how will this equation look like? The first equation will be simply del square V equal to minus rho by epsilon 0. So that this difficult equation has been reduced into a much more simpler equation, the Poisson's equation in this case. So that is the meaning of applying a Coulomb gauge or a Lorentz gauge. We can simplify these equations. Now as an assignment, try to substitute Lorentz gauge into these reduced Maxwell's equation and then reformulate the equation. Now pause this video, try to apply the Lorentz gauge into the reduced Maxwell's equation and write down the final equations. So what have you got there? You might have obtained del square A bar minus mu 0 epsilon 0 dou square A bar by dou t square is equal to minus mu 0 j. Similarly, for the second equation, if you substitute the Lorentz gauge, you can obtain del square V minus mu 0 epsilon 0 dou square V by dou t square is equal to minus rho by epsilon 0. So these equations are much more simpler, and even look at that beauty of those equations. Those equations are very beautiful. I will rewrite those equations now. You can see that they have something in common, right? So I can define a new operator, new differential operator. Its name is quabla, and quabla is given by, or it's called box square, and I define this box square as del square minus mu 0 epsilon 0 dou square by dou t square. So it is a new operator consisting of both spatial differentiation and time differentiation. So it is del box square is equal to del square minus mu 0 epsilon 0 dou square by dou t square. So if you put this quabla into this equation, try to substitute quabla into this equation, how will these equations look like? So our new equations will be quabla square or box square V is equal to minus rho by epsilon 0, and box square A is equal to minus mu 0 j. So these are very beautiful equations, right? The simplicity and the structure of these equations are very beautiful. And what are these equations? These equations are simply Maxwell's equations in a summarized form. What have we done? We took the 4 Maxwell's equations, we substituted 2 equations into the other one and got the reduced Maxwell's equation. Then we used some gauge transformation, some Coulomb gauge and Lorentz gauge, and applied into that equation to get a simplified form. And that equations are these equations. So these equations are called inhomogeneous wave equations. Inhomogeneous wave equations. And these equations contain everything about the basic electrodynamic concept. The Maxwell's equations are actually contained in these equations, and we can use these 2 equations to work out any problem relating to electrodynamics. So in the coming classes, we will be using these inhomogeneous wave equations, and we will start by stating the solutions of this inhomogeneous wave equation. All you need to remember is that they are simply Maxwell's equations itself. We have applied some small changes here and there, like we have brought a reduced form, then we have applied some gauges, some Coulomb gauge and Lorentz gauge, and the Maxwell's equations were reformulated into the inhomogeneous wave equation. So these are just brief introductory ideas. Maybe you have some doubts here and there. I have quickly gone through a lot of portion, a variety of portion, I know that, but I think this gives you a basic concept about what we are going to say in the next class. We will be all of a sudden beginning with the retarded potentials. For that you need to have a concept about inhomogeneous wave equation. I hope that you got an understanding that those are just Maxwell's equations written in a more detailed manner by reducing those equations and by adding certain conditions. I hope this portion is clear for you. Thank you.